So last time we, well, the general topic that we have been considering for some time is, so what are the effects of the properties of the electromagnetic wave which crosses a region filled up with either just cold plasma or plasma and a magnetic field. So the main effects, which are the dispersion measure, which is due to the fact that at higher frequencies, the group velocity is faster, is higher. So you have the dispersion. So the plasma is a dispersive medium, and so for an impulsive signal, like a burst, for example, and I will make an example either today or next class of an astrophysical source, which are ideal from this point of view. So you get first, but we already mentioned the example of the galactic pulsars. So you first receive the impulse at correspondingly larger frequency, and then the delay scales as 1 over gamma square, nu square. Nu is the frequency. We also saw, I'm just making a kind of summary, the Faraday rotation, which is what happens in the presence of both plasma and an external magnetic field. In particular, we saw that what is relevant is the parallel component of the magnetic field, parallel with respect to the line of sight. And in particular, it's also sensitive to the sign. So whether it is anti-parallel or parallel. So a fair example of this application is just the mapping of the galactic magnetic field. And also, we also mentioned the kind of radiation that you should expect in the presence of relativistic particles moving within media. So in particular, when the velocity of the particle overtakes the velocity of light in the medium. So Cherenkov radiation and the raising effect, which affects in particular the synchrotron spectrum at lower frequency. So today we see another effect which is pretty different from the previous ones, but this is very important because again it's a signature. It's a signature of what the plasma can leave on the electromagnetic wave of a source which lies beyond the plasma or behind from our point of view as observers, in particular due to the irregularities. So, okay, this is just a brief summary. So the group velocity so depends on the frequency. So the medium is dispersed in this way, where omega p is the plasma frequency. So as long as you might consider a wave crossing a region with a variable density, since the plasma frequency does depend on the density, you might end up, so the variability, some variations, spatial variations in the electron density reflects into corresponding variations in the refractive index, and so on the velocity groups. So what we aim to study today is to see the effect once you have a kind of screen, so a region which can be relatively thin, within which you have some plasma irregularities. So plasma whose density is a function of the point in space, so changes according to some given pattern. And of course, this affects the propagation of, for example, a plane wave. We will see what happens. In particular, we will study the effect of both the refraction and diffraction, in the sense that what we will be focusing on is we will consider a medium with some, as I say, you can think of a clumpy medium, so medium made up with blobs, each of which is characterized by a different, slightly different refractive index due to a different electrons density. Okay, so we will see essentially how the plane wave crossing this region is affected. We will consider both, as I said, the refraction, so the fact that a plane wave at some point is crossing a region with a different density, so a different velocity, through the medium. And so, as a matter of fact, we will see that there is a change in the direction of propagation of the wavefronts, as well as the diffraction as the result of the wavefront which is affected by this fact. In particular, we will consider there are some different models. We will focus on one of them, not because it's particularly more important than the others, but because it's representative of essentially the main effects that come into play, which is called the Gaussian screen model. Okay, these are just comments that will become clear in the following. So this figure just tells us everything about what this model is about. So here above, you have an incident plane wave, so an electromagnetic wave generated by some given source, which is far away, which lies far away from this. We are here, we observe here on the bottom, and at some point this plane wave crosses this region you see here, filled up with kind of blobs, and the width of this region is relatively thin. And all these blobs, whose typical size is we call A, so A is just representative, is just telling us about how big typically these blobs are. And so these blobs are characterized by having a different, by having some changes in the plasma density, so changes in the refractive index. So as a matter of fact, the result is that the wave front coming out after crossing this region is just kind of bumpy. It's just crinkled. It's no more straight. So as a matter of fact, all this wave front has essentially two effects. One is the fact that the image that you get of the source that is responsible for the electromagnetic wave is kind of distorted, and in particular, you get sensitive. The image gets and the flux you measure for the source becomes sensitive also to the possible turbulence or relative motion of this medium, these blobs, with respect to the observer and to the source. So if there is relative motion, of course, the flux as well as the image will be affected as a consequence. And also we will see that there is also a frequency dependence on this wave. In particular, okay, so the first thing to note is, just as I said, that the wavefront gets distorted and gets crinkled, kind of crinkled. The second effect is that, and so this is the result of the different processing of the refraction process taking place in these blobs. The second one, you see that there is some variance in the angle of all these rays as a consequence of this fact. So they will interfere at some distance, so creating a pattern, an interference pattern, due to the diffraction, essentially, of all these rays. And we will see that, essentially, if you could ideally move along the plane perpendicular to the line of sight, your detector, in this case, this is kind of radio telescope, because this is particularly relevant in radio band. But, so if you think of a generic detector, you can move along this line, so within the plane perpendicular to the line of sight. You will see that if you measure the flux, you will see some kind of fluctuations due to the different interference that you've got as a result of all these rays, which are no more parallel in general. Of course, you have to consider that this is a kind of random process. Random because the number of blobs that each ray is going to cross is something which can be considered as a stochastic process, so as a random process. So there will be rays which are more deflected than the others which gets undeflected at all. So due to this, you can have a pretty complex interference pattern, or better, diffraction pattern, and this is a snapshot. So if you just imagine you freeze all these blobs, but then if you add also the possibility that they can be moving also, for example, because the medium, the screen is turbulent, so there is turbulent motion. So you see also variability also if you fix the position of your detector, because the diffraction pattern at some given point changes as a function of time. So we will kind of model all this to see what can be inferred. Yes, in particular, yeah, okay, this is just a comment on what I just said. So let's be more quantitative, and let's start from what we know very well by now, which is the refractive index n as a function of nr, not to be confused with n, which is, I remind you, is the particle density. Okay, so this is something we already saw repeatedly. So let's also remind ourselves what the plasma frequency, so in particular, the plasma frequency square is 4 pi n e square over m, where all these constants just refer to the electron, because that's the most that's the particle which has the most favorable ratio between charge, electric charge, and mass. And n, as I told you, is the plasma density, number density, so number of electrons per unit volume. And here omega is just the angular frequency, so 2 pi nu. Okay, so if you manage also to express instead of nu as c over lambda, so you have c over lambda here, and you see here you recognize an old friend of us, which is e squared over mc squared. If you remember, this is the electron's classical radius, which we called at the time when we were speaking about Thomson scattering in particular, Re. So Re is the classical radius of the electrons, and this is also useful because it allows us to immediately not only to see the quantity itself, but also from a dimensional point of view. You immediately see that this is a length times a length square, so length cube times 1 over length 1 over volume. So indeed, this is just dimensionless as it is to be. This is a refractive index. So let's consider, as I told you, we are interested in evaluating, in exploring the consequences of a medium here, of this screen, thin screen, characterized by an inhomogeneous plasma density. So in particular, let's evaluate the consequences of delta n, where delta n is the typical variation in the density. So as a consequence, we have this variation in the refractive index, which you immediately see depends also on lambda squared. So it's particularly sensitive on the wavelength. So again, we follow essentially, in order to evaluate the consequent phase shift. If you consider the same path traveled by a wave, considering two different wavelengths, so we want to determine the phase shift between the two waves. So same path, so they cross the same. They cross the same path, but they of course are characterized by different wavelengths. So what is the corresponding phase shift? Well, we have to go through the corresponding change in the wave number, very much the same way, the same line of reasoning we followed last time when we were talking about Faraday radiation. So k, then the wave number is just omega over the velocity, the speed of light in the medium. So c over the refractive index. Omega is just 2 pi nu. C over nu is just lambda, okay, so 2 pi over lambda times the refractive index. So you calculate the change, so the change of the refractive index, which is exactly what we got here as a function of the change in the density, corresponds to this change in the wave number. So by replacing, you replace in this guy. And here you see, here you have 1 over lambda, and here lambda squared, so you're left with lambda. And then you have 2 pi here at the denominator, so they just cancel out. So delta k is just the radius of the electron times lambda times delta. Here I just put the the absolute value. I'm not interested in the sign because of the reasons that you're going to see in a moment. So, okay, this is just a relation we've come up with. So how can we estimate the phase shift? Well, if the path traveled by the wave is the same, in particular, we consider the typical blob size. As I said, A is the typical size. So if you imagine these two waves crossing the same blob, it means that because of the different wave number, the consequence is, of course, the corresponding phase shift is just wave number times the length traveled. The length traveled here is A. They are just crossing the same blob. So delta phi 1, where delta phi 1 means the phase shift due to the crossing of one single blob, okay, is just delta k times the traveled length, A. So this guy times A is this guy here. But, well, you can imagine that while A tells us about the typical size of one single blob, this screen is made up with several blobs. And in particular, if we call L the overall thickness, so this height here, okay, so the overall thickness of this screen, of this medium, you can imagine more or less that if you neglect the spaces in between the different blobs, so just imagine they are just all packed close to one another. So more or less, the average number of blobs that a generic wave will encounter, so the ray will encounter while crossing this screen, will be just more or less the total width over the size of a single blob. Here, about equal. It's an estimate of the average expected number of. Of course, it's a random process because we assume that they are randomly distributed. All these blobs are more or less randomly distributed. Okay. And so, given that this is a random process, what the number of blobs that each single ray will cross, it makes sense to estimate the so-called root mean square. So it's the square root of the variance of this number. In particular, it's a Poisson process. So you know that in a Poisson process, if the expected number is n, well, the corresponding standard deviation, so the root mean square, is just the square root of n. So it means that given that you imagine one single ray crossing different blobs, well, the crossing of one single blob is independent of what happens next and as well as of what happened before. So all the individual crossings of all the individual blobs are independent of one another. So it means that this is indeed a stochastic process in which the expected variance, or better, root mean square, so the standard deviation, scales as what? Well, all the individual phase shift that you expect in the crossing of one single blobs times the corresponding root mean square in the number of blobs. So they will fluctuate according to more or less to square root of n, where we implicitly assume that n is considerably large, not too small. So the cumulative phase shift, root mean square in the phase shift. So while the average phase shift will be n times delta phi 1, we are interested in the kind of noise, let me say, statistical noise. So in the wave, this number will be distributed, will be scattered. So the average value will be n times delta phi 1 with a scatter of what? Of what I called here delta phi, which is exactly what we are mostly interested in. So this guy is telling us the typical difference between all the rays in terms of direction of propagation when they come out of the screen. So if I could calculate the angle due to all the points here along this crinkled wavefront, and I calculate the distribution of the angle, and then I calculate the deviation, the standard deviation of all this angle, what I come up with is something like comparable with delta phi. Okay, so delta phi, the higher delta phi and the more crinkled is the wave number. So in particular, okay, just replacing, you see that given that square root of n is the square root of L over A, you multiply by A, which is in delta phi 1. So in the end, this guy becomes square root of L times A. Times what? Well, times the typical delta n, where delta n is the typical density variation inside one blob with respect to outside. Okay. Of course, if there were no density in homogeneities, well, delta n would be 0, and that would be a perfectly homogeneous screen. So essentially, there would be no effect in this, in making this the wavefront just bumpy as it is. Okay, this is something that I already said. So now the goal we set to ourselves is to determine the typical angle, which I call theta s, by which all these rays are tilted. Okay, so as a matter of fact, due to this screen, should there were no screen, all the rays will just propagate straight away along the line of sight. But because of this, they are just tilted. Of course, it's a random process, as I said. So the tilting angle varies in a random way from individual rays. But what we can use to characterize the average property is just the root mean square. So the average angle by which we call theta s, by which these rays are tilted with respect to the line of sight. Okay, and in particular, if the phase, okay, we'll see. So let's see now more in detail what happens. So let's consider one single blob. So let's focus here on the top panel, on the top figure. So here I just wanted to represent one single blob, which I ideally represent this as just a sphere. So this is a wavefront which is going through, and as a matter of fact, you see, given that the rays crossing, so we aim to compare what happens between two rays. The rays here which crosses the blob and the one here which doesn't. So there will be a phase shift due to the fact that the propagation here is different. In particular, we calculated delta phi. So the resulting delta phi, I should call here delta phi 1, but let's assume then, okay, we will see that then we can consider the cumulative. So delta phi 1 here, or delta phi, is just the phase shift of this wave with respect to this one. In terms of phase, in terms of corresponding wavelength, well, the phase with respect to the total phase over 2 pi is this ratio here. So delta phi over 2 pi is the relative shift with respect to one period, one wavelength in terms of spatial periodicity, multiplied by lambda. This tells you the path that has the difference in path between the two equal phases. So if you want to have the same phase between this ray and this ray, you have to add an extra path, which corresponds to delta phi over 2 pi times lambda. By adding this, you recover the new wave front. I remind you, the wave front is the locus of points at which the phase is the same. So it means that here you have a phase shift. So if you want to recover the same phase as here, you have to add an extra path. What is this path? This path is lambda times the fraction of the period, which is given by the fraction of the extra phase. So delta phi over 2 pi times lambda. So this is the path that you have, by which the wave front has changed orientation. So let's calculate this. In particular, as I told you, delta theta s is the angle by which the wavefront, which was here, has been rotated. So has been rotated from this to this. So this is indeed the angle I'm looking for. So let's calculate. Well, consider that, just for the sake of clarity, I had to make this drawing clear. So I have to show you big angles. But as a matter of fact, the fluctuations in density are relatively small, as well as the typical in typical realistic situations. So these angles are very small. So you immediately see that this side. This is a rectangle triangle. So you know this side, you know this side. This is just a over 2. This is just 1a, so a over 2. This is delta phi over 2 pi lambda. So the tangent of this angle, the tangent of theta s, is just this guy over this guy. But the tangent of a very small angle equals the angle itself in radiant. So as a matter of fact, theta s is just this guy over this guy. So this guy here over a half. So immediately see that the angle by which the wavefront has been tilted due to this effect, can be estimated like this. Here I already put the total, the overall, yes, because, well, not the total, the root mean square, because as I said, this process works in an independent way. Each blob is independent of the other, of the next one, if any. So that's why the cumulative effect depends on the root mean square of the angle. Because, for example, you can have the crossing of two blobs, which one deviates in one direction and then in the other direction. So the net effect is 0 in one case, for example. So that's why, in the end, the cumulative sum depends on the square root of n. More or less the same. It's like if you remember when we considered the random scatterings, multiple scatterings. In the end, the number of scatterings, we found out that was scaling as the optical depth squared in the case of optical depth very large. So this is just the same line of reasoning at play. So that's why here I just consider the cumulative effect. If you consider just delta phi 1 and then you multiply the result for the root mean square of delta phi, the result is just the same. So the cumulative effect in this tilting of the wavefront is this guy here. So on average, you will see that the wavefront has changed as a variable direction, which this scatter. So this means is on a practical basis, if you could imagine, you can pick up two rays randomly and you work out the difference in their tilting directions, you will find something comparable with this guy here. That's the meaning of this delta phi. Okay, so just using the delta phi we've come up with in the previous slide, which was the guy here. So the guy here I reported here. So the resulting, by multiplying this by lambda over pi a, you see that you gain an extra factor of lambda, so lambda square, the radius of the electron. And again, here you have a square root of L A over A, so a square root of L over A. And it is it scales directly with the variability in the plasma density. So in particular, notice that it scales with it is frequency dependent. So if you fix the very same screen and you consider wavelengths with different waves with different wavelengths, this effect is amplified by a factor of lambda square when you move to lower frequencies, to lower frequencies. This holds as long as you have a source. So this is theta s is what you observe. Is essentially, in particular, is the size, the angular size of the source as seen from your point of view as an observer due to this different scatter in the refractive properties of the medium. This holds as long as you consider a source which lies very far away from the screen. Why? Because in this case you do not consider you consider the incoming waves as just plane waves. But this holds as long as you consider, as I said, the source of electromagnetic wave, which is extremely far away from the source. If this is not the case, and this is the meaning of the figure below, so let's consider here is the observer and here is the source. You immediately see that here is the screen responsible for this affected, characterized by the variations in the plasma density, and so responsible for this refractive process, variable refractive process. Let's call r prime the distance between the screen and the source. So in this case, in the case above, essentially r prime is very large, but very large doesn't mean really anything. You have to compare with what? Well, compare with the distance between the screen itself and the observer, which we call r, capital R. So this is the case as long as r is as r prime is much larger, much greater than r. If this is not the case, as in this figure here, you see that the two are comparable. R prime is not negligible with respect to r. Well, in that case, just for geometry reasons, you see that indeed, if just consider this ray. Suppose this ray has been tilted by theta s, which is exactly what we calculated here. But what you observe is not theta s, but is theta s prime, okay? Just because of this geometry here. So it means that, as a matter of fact, that you have to correct what you measure is theta s prime, not theta s. So in order to do that, again, this figure here shows you angles which are pretty large. But as a matter of fact, this is just for the sake of clarity of the figure. As a matter of fact, you should assume that both theta s and theta s prime are very small angles. So how can you calculate theta s prime? Well, just have to use the sines law. So from basic geometry, if you consider, let's apply the sines law with this couple of angles here and the one here, which is telling us that the ratio between the sine of this angle here and the opposite side, so this guy here, equals the ratio between the sine of this angle here over this side here. But this side here can be taken as this side here, just because this angle is very small. So the error that you make by taking this instead of this is very small. Essentially, there is a cosine of a small angle, so you know that there is a second order in the Taylor expansion effect. So you can just take this guy as this guy, so you have indeed that theta s prime over what? Over this guy, but I said you can take this, so theta s prime over r prime equals, well, the sine of this guy, well, the sine of one angle is equals the sine of 180 degrees minus minus it. So the sine of this guy is equals the sine of theta s. So theta s, because we are talking about small angles, so theta s over all this side, which is just r prime plus r. So you see that essentially what you measure in the case of a distance between, you have two distances essentially. Distance between screen and source, and screen and observer. When the two distances are, one is not negligible compared with the other, you have to correct by this factor here. And you immediately see that, yes, this indeed, this angle here is diminished as long as if the screen is moved towards the source. Indeed, if you imagine you fix the distance between the source and the observer, and you ideally move the screen towards the source, you see that, well, the sum here, the denominator is the same or changes is r prime, which gets progressively smaller. And so is the effect of the scattering that you observe. You measure theta s prime, while theta s is just due to the properties of the screen. So L, A, delta n all depends on the screen. Lambda, well, that is the only thing that depends on the wave you have in mind. Okay, so essentially it's just fixing the distance between the observer and source, fixing the properties and the size of the screen. If you imagine you can move the screen towards the source, you kind of quench, you suppress correspondingly this way this effect, even if the tilting is the same, you see, from the point of view of what happens within the medium. Yes, so let's calculate again what are the effect in terms of, so far, just to summarize what we did so far. So far we calculated, due to the refraction properties of the medium, to the variable refraction properties of the medium, we saw that in general, when, again, let's suppose the source is far away, we have a plane wave, and the plane wave is just distorted, it just gets crinkled this way. Just because of that, we neglected the diffraction taking place within the screen. Okay, now let's consider instead the diffraction effect, because you have different rays with different directions, and we calculated the typical difference between, in terms of angle, between all these rays, theta s, and then theta s prime if you consider the observer. So we can ask ourselves, at what distance these rays will typically cross? So we'll come together. Why do we ask this question? Well, when this condition is fulfilled, it means that here you might have either destructive or constructive interference. So you have a signal which can change significantly depending on the position you move along the plane which is perpendicular to the line of sight. Of course, given that these rays have an angle between themselves, which has been already determined, of course, you have to, there will be a minimum distance below which you have, all these rays cannot come together. So in particular, it depends on both the angle, theta s, which you already calculated, but also on the minimum size here. And the minimum size here in the screen is just the size of one single blob. That's the only possibility, that you have two different rays with a difference in the angle comparable with theta s. So if you consider ideally a small triangle with a base here of length a and an angle here, theta s, you can immediately calculate what we can call as a critical distance, which I call RF. Well, RF is this distance here. You know this angle here, which is theta s prime. Let's just consider the point of view of the observer. So given that here the size, the minimum size, is the size of the blob, so just geometry for kids, you immediately see that given that R times the angle has to be the length here, A. So RF times theta prime has to be equal A, has to equal A. So this critical distance beyond which, so if you measure this distance from here, from the screen towards the observer, it means that you will see all these patterns, all these complex diffraction patterns at a distance which has to be larger than the critical distance. Okay. Otherwise, if you are too close to the screen, there's no way all these rays coming out of the screen can come together. It can interfere in a constructive or destructive way. So this is just the first thing to note. So provided that the observer lies beyond the critical distance, in that case, you are expected to see all these complex patterns. You see that this resulting electric field that you measure can be varies as a consequence. So it's a diffraction. If you calculate, so for example, the flux as a function of the position along this plane here, what you get is the so-called diffraction pattern. Depending on this is a diffraction process because you have different rays just traveling with different from different position with different angles, so they just interfere in a very different way. And considering that also this process is just due to a random distribution of all these rays, because they inherited the randomness of the distribution of the blobs. What you know, so you cannot infer anything about one single ray, but you know the distribution of the properties of all these rays. You know that they are distributed with a scattering in the angle comparable to theta s prime. Okay, so this is what you know, and this is important because this allows us to calculate the so-called well, as I already told you. So what the diffraction pattern is just the result of this diffraction figure along the plane which is perpendicular to the line of sight. So depending on the kind of interference that you've got at any single point, you have a different resulting electric field, so different intensity. It works more exactly in the same way as what you already know from Fraunhofer diffraction. Here, of course, what is responsible for the diffraction process is just this screen, which has distorted the wavefront in such a way that then you have, as a consequence, all this complex, in general, complex diffraction pattern. Complex just because it reflects, as I said, the randomness of the distribution of all these blobs. What you can use to characterize this diffraction pattern is the so-called correlation length. What is that? Well, imagine you can move your detector along this direction, okay? So you will see that there is a correlation between the signal. So it means that if you move from a very, very small, from a tiny length along this direction, you are not expected to see, if the displacement is sufficiently small, you are not expected to see a big change in the average intensity, so in the diffraction pattern. So it means that there will be some distance, typical distance, beyond which then there is no more correlation. So no more relation between the average intensity in one point and the average intensity measured at a different point. So this is so-called correlation length. So it reflects the the amount of correlation between the diffraction within the diffraction pattern. From a mathematical point of view, this is something that you can calculate with a so-called autocorrelation function. It tells you essentially the memory between the intensity, in this case, of the signal between two any points. If you consider 2 points which are too far away from each other, but there's no correlation at all, you cannot, means that you cannot predict the average intensity in one point if you know the other one. This makes sense if you consider the randomness of the process. But if you take them close enough, of course, at some point, provided that you take them very close, the intensity cannot change too widely between them. So in that case, it means that there is a correlation. In that case, it means that if you know the intensity in one point, you can immediately estimate the intensity in one point. So it means that provided that you consider 2 points along this direction, which are close enough, there is some kind of memory between the intensity in the 2 points. But there is also, so you infer comparing the 2 extreme cases, so very close and very far away points, it means that there is an intermediate distance which somehow works as a critical distance. So below which there is correlation, beyond which there is no more correlation. This is indeed the correlation length, which we call DC. And what is that? Well, now the figure below, the bottom figure, helps us to figure out, to calculate, to estimate the correlation length. Let's see why. Well, you see that all these rays, the maximum, the typical angular tilted angle between these 2 any rays cannot be larger than theta s prime, okay, from the point of view of the observer. So it means that you will be expected, if you ideally, okay, this is a vertical line, is the this is the same drawing but different, as seen from a different perspective. You see, this is the source, so this is the plane I'm considering, so the plane along which I measure the diffraction pattern. So because this is the plane perpendicular to the line of sight, which is this one here, okay. So ideally, if you could move your detector along this plane, so you would see that, okay, you measure the correlation, the diffraction pattern, so intensity changing as a function of the position. We want to calculate the correlation length. But this means that you will have no correlation between one point here, for example, and another point here, as soon as the difference in the travel path by the wave gets comparable to what? To lambda itself. Because in that case, the shift, the phase shift, is so big that, of course, you might have destructive interference or comparable with. Okay, so if I want to measure the correlation length, I have to take 2 rays for whose corresponding paths differ from one another by a quantity, by a spatial quantity, which is comparable with lambda. But you see here, the two any rays that you consider, their corresponding angle cannot be, their difference cannot be larger than theta s prime. So if you want a path from this line here and this line here, which differs by a quantity comparable with lambda, this path here, and at the same time the angular difference between the 2 rays is of the order of theta s prime, it means that you have to consider this triangle here. And this immediately determines the corresponding length along the plane. So you will be expected to see no more correlation along this direction as soon as corresponding to an angle here, theta s prime, you will have a difference in the path traveled by the 2 waves of the order of lambda, which is here. So you've got this, you've got the angle, so you immediately determine this quantity here. And if you immediately notice that lambda has to be equal to dc times sine of this angle here. But again, we are talking about small angles, so the sine of this angle is the angle itself in radian. And so dc times theta s prime is lambda, so dc is lambda over theta s prime. So lambda is a property of the wave you have in mind. Theta s prime is determined by the scattering process, by the refractive processes, so by the inhomogeneities in the density of the screen, and the distances between source, screen, and observers. So in the end, you see this, you calculate this correlation length. So the correlation length tells you, okay, if you move your detector along this plane by a distance which is smaller, which is negligible, or much smaller than the correlation length, you see essentially a very small change in the intensity. So in the diffraction pattern. Okay. But instead, if you move your detector by a length which gets comparable with DC or even larger, then you will collect the flux will change. So the intensity, the average intensity that you can measure, changes completely. So it is no more correlated between one point and another. So it means that it changes significantly. Well, this is important because if we allow the medium, which is responsible for this effect, so the medium within the screen, to change as a function of time, which, as I said, could be the case of a turbulent medium, so a medium in which all these blobs are moving randomly and they are just subject to, and whose motion, for example, can be characterized with a typical velocity, which I call here Vs. Well, what happens? Well, you see that because of the geometry itself, if the blob responsible, for example, for this ray here tilted this way moves, well, then all these angles moves, and so also the corresponding point at which the diffracted ray arrives on the detector plane. So it means that ideally all the diffraction pattern can shift along this way. But by shifting the diffraction pattern, if you keep your detector fixed, it means that it is equivalent as if you were moving the detector along this plane. So at some point you are expected to see variations in the flux that you measure because the screen here is moving. Okay, so if we call tau d the time scales that I have to consider, so how long am I expected to wait for to see a significant variation in the intensity of measured by my detector due to the motion, to the relative motion. In the end, it's a relative motion of the source of the screen with respect to the source and observer. So I can calculate, I can estimate the time scale that I have to wait, that I have to consider, the time interval over which I will be expected to see a significant variation in the flux. So what is called the scintillation. Scintillation is the flux which is varying with time significantly. So the variation in flux are comparable with the flux itself. So you can see, as from an observation point of view, you see the flux varying widely or significantly. How can I estimate this? Well, if this guy moves here, for example, in this, let's consider Vs as the typical velocity of the screen in this way, so perpendicular to the line of sight. Well, delta theta is the angle, is the change, is the consequence change, consequent due to the motion of the blob here. Delta theta is the angle here, which is, if I consider a time interval tau d, which is in the end the only quantity I want to calculate, but let's consider, just for the time being, a time interval tau d. Well, if I consider this time interval, the position of the blob will have changed by an amount which is Vs tau d along this way. But the corresponding change in the angle of this ray with respect to the line of sight is delta theta is what? Well, again, I remind you, these are small angle, is just this length over the distance, r prime. Okay, r prime is just equal to this, small angles. So then, if I call delta theta the angle by which this ray is rotated, well, that's exactly this ratio here. So the displacement here over the distance, r prime, so this ratio. But I want to calculate, what I'm interested in is the consequent displacement on this plane. And in that case, given that the angle is the same, imagine you rigidly rotate, you rigidly tilt all this rays here, so also this tilted ray here. So this will move as a consequence. But this is at a distance which is r prime plus r from the source. So given that the angle by which this ray is also tilted is the same, delta theta, dc, which is the direction I want to consider along this plane here, is the ratio between dc over what? Over the distance between the plane here and the source, r plus r prime. Why I use dc, which is the correlation length? Because I want tau d, so the time interval, to be large enough, or yes, to be enough that the displacement, the consequent displacement along this plane is indeed comparable to the correlation length. Why do I want this? Because only when the displacement in the position of this ray due to the motion of the blob will be comparable with the correlation length, only in that case my detector will be sensitive enough to measure a significant fluctuation in the flux. It is for the very same reason I told you before when I was defining the correlation length. If you move your detector by a small quantity, small compared with the correlation length, you will see a negligible, very small flux variation. In order to see a variation, you have to move, when all here is fixed, you have to move by a length which is at least comparable with the correlation length. And here, you're not moving anything. Your detector is fixed. What is changing configuration is due to the motion of the blob. So you're now demanding, I want to wait a long enough time interval, which I call tau d, such that the consequent displacement of the diffraction pattern here gets comparable to the correlation length, dc. If that is the case, then my detector, which is at a fixed position, will measure over that time interval, will measure a significant fluctuation in the flux. So that's why I called tau d. So if tau d satisfies this condition, and we immediately calculate that tau d is just multiplied by r prime over vs, both sides of this equation, you immediately have a condition of tau d. So tau d is the time interval over which your detector will measure a significant variation in the flux. So that's why we call variability time scale. And you see, well, it depends on the velocity of the medium. Of course, the faster and the shorter. Of course, the faster this moves, and the correspondingly shorter the time interval in which the fluctuation will be observed here. So it also makes sense from a qualitative point of view. And okay, just by using the definition, well, not the definition, but the value for the correlation length, which is lambda over delta theta s prime. So I just here replace instead of dc this guy here. So lambda over theta s prime. I slightly rearranged the terms in such a way that you see here, this guy here is nothing but theta s. If you get to the previous slide, we found that theta s prime indeed is r prime over the total sum of the distance over times theta s. So all this guy here is nothing but theta s. So again, you immediately see that in the case of turbulent, I say turbulent, so in which all the blobs will be moving with the typical velocity, which is vs, for example, the more turbulent and the more fluctuating will be the flux measured by the detector. Or better, rather than more fluctuating, it will be fluctuating on a correspondingly shorter time scale. The faster, so the higher v, and for some fixed properties of the medium at a fixed wavelength, and the shorter the corresponding variability timescale. So by measuring the variability timescale, you can also infer on the properties of the turbulence of the medium, which is responsible for this effect. There is also another aspect to consider. Let's suppose we have two rays, one which gets through the medium in an unscattered way, so just along the line of sight, and another one at the same wavelength I'm considering, which is then traveling over a longer path, is up to here and then is refracted and then just goes here, and the two combines here. Well, it is interesting to calculate the difference, the delay between these two rays. Let's suppose they are emitted at the same time from the source, but of course this says the red ones has to travel a longer path, so there will be a delay at the arrival time at the observer. Let's calculate this. In particular, we calculate this delay as tau c. So due to this geometry here with respect to the unscattered, so the straight line along the line of sight, I'm using some identities in vector calculus, so very simple. So that's why I call two vectors A and B. And you immediately see that the light travel time, the difference in the light travel time between the two rays is, well, on one side is the unscattered ray just travels along this guy here, but this guy here is the modulus of A minus B vector. Just simple difference between two vectors, which is exactly this guy here. While the ray which travels for a longer time is just the modulus of A plus the modulus of B, so A plus B. So the difference between the two is just the delay in the arrival times times the speed of light, of course. Speed of light in vacuum, because here is vacuum, here is vacuum. Okay, the screen is relatively thin. It has an important effect on the tilting the rays, on refracting the rays, but then the light travel time is mostly determined by empty region here. So let's calculate just very simple stuff. So this guy here is just would be minus cosine of the angle in between, but minus cosine is plus cosine of this angle here. So plus cosine of theta s. Yes, this is theta s. Here I just added and removed 2ab, so you can build up here the square a plus b all squared, and then minus this guy here. And you can collect the term a plus b. So a plus b, this guy, open bracket, here you have 1, here you take a plus b squared out of the square root argument, so you have 1 minus 2, all this guy here over a plus b squared. Now, remember that this quantity here, the cosine of theta s is a very small angle, so the cosine is very close to 1. So it means 1 minus, it means that it's a very small quantity with respect to 1. So it means that you can Taylor expand square root of 1 minus something small, which is 1 minus 1/2, that's something small. So 1/2, you have 2 here, 1 over half, so the 2 just vanishes, and you're left with 1 minus, so 1 plus, minus 1 plus this guy here. Again, we Taylor expand again, as I said, for the very same reason I told you. So cosine of a small angle, you can Taylor expand 1 minus theta squared half. Given that here there's a minus sign, so minus 1 plus theta squared s over 2. So you are in the end, you are left with a small quantity. Yes, of course, that's what I expected, given that here the drawing can be a little bit deceptive, but just for the sake of clarity, we are talking about very small angles. So of course, the delay with respect to the light travel time will be relatively short. In particular, it scales with AB with theta b theta as a square. So the delay between the two, which we called tau c, as this guy here, where let's give proper names. So A and B is nothing but the modulus of A is R prime. Again, I'm using the same. I'm exploiting once more the fact that we are talking about small angles, so you can confuse. You can take this one instead of this one, and here the same. So instead of B, you take R. Instead of A, you take R prime. And so you end up with this guy here. What I can see here is that, for example, if you fix the distance between source and observer, so you fix R plus R prime, and you imagine you move the screen in between, you might wonder what is the position of the screen which maximizes DC. Well, this is an exercise for first year undergraduate students, but if you have well, you can calculate with just a simple derivative. If you are smart enough, you see that the privileged, the special position is when the two, when R and R prime are equal. That is the case which maximizes the time delay. So where it just lies exactly in the middle. And why is this quantity interesting? Because you see, if you have a delay between the two rays, so this one and this one, which is the quantity we just calculated, and you imagine in terms of phase shift, you have a temporal delay. So if you multiply omega, you remember the argument of an harmonic wave. So it means that the shift in the phase will be omega delta t, where delta t is what we call in this case tau c. So the shift, the phase shift between the two waves, due to the fact that they travel different paths, is what? Well, is omega tau, so 2 pi nu, where nu is the frequency, Tc. So in particular, so there will be some kind of interference due to the phase shift. But if you now imagine to consider a range in frequency, so let's consider many different frequencies in a continuous range, which we call delta nu c. Well, you might wonder, you immediately see that the corresponding change, so if you consider two different frequencies whose separation is delta nu c, well, the corresponding phase shift will be 2 pi delta nu dc. So you might wonder, what is the wave, what is the delta nu, so the interval between the two frequencies, such that the phase shift between the two frequencies changes by 2 pi. Why in this case? Because if you imagine your detector is integrating the signal within a frequency range, which is essentially what every detector in practice does, because you cannot measure you cannot measure this specific flux. The specific flux is so the flux density at one single frequency. What you measure, as a matter of fact, is always power integrated along within a bandwidth, so within a frequency interval. And then when you want to calculate the flux density, of course, you take the power and you divide by the frequency bandwidth, so by delta nu. But what you measure is always a specific intensity integrated within a bandwidth, so within a frequency interval. So if the frequency interval along which you are integrating the signal is such that the kind of interference between two rays having the same frequency but having traveled the different paths changes significantly, how much? For example, by 2 pi, it means that you are summing up the signal of different frequencies whose interference is different. So they cancel each other. So in particular, so because of that, by demanding that 2 pi delta nu c times tau equals 2 pi, you end up with a condition that delta nu c equals tau c. So what is delta nu c? So delta nu c, which is called correlation or scintillation bandwidth, is the bandwidth, so the frequency interval over which you have more or less the same, essentially the same kind of interference. So either constructive or destructive. So all the frequencies within that frequency interval, they interfere the same way. So you have an enhancement in the signal. If you integrate over a frequency interval which is much larger than this guy, it means that then you are summing up different kind of interference. So you are just smoothing out possible variations. So it's a correlation bandwidth because it's the frequency range in which you have all the same behavior, all the same kind of interference between the rays traveling different paths. Okay. And of course, yes, because of the condition I just told you. So 2 pi delta nu tau equals 2 pi, it means delta nu equals 1 over tau. So this is called correlation, or as I said, scintillation bandwidth. Why scintillation? Because as a matter of fact, when you integrate over such a frequency interval, you are still capable of seeing the flux which fluctuated if it is the case as I was mentioning before. So for example, if the blobs responsible for this are moving. So provided that you integrate along a bandwidth which is comparable or not larger than delta nu c. So in this case here, I just calculated, as I said, the case which maximizes tau c, or equivalently, which minimizes delta nu c, the bandwidth, which is the case in which the two are equals. So r equals r prime. And the corresponding, so, okay, so in this case is just this guy here. Rs is the distance between source and observer, so the sum of the two. So in this very case, this is the general case, in which you make no assumption on r and r prime. This is the equality case, in which the two are equals, of course. You remember that if you get a few slides ago, you see that delta s, theta s, sorry, so the tilting angle due to the screening properties, so of the medium, is something which scales, so theta s scales with lambda squared, is a result that we obtained. So here is squared, so lambda squared, it means that delta nu scales as 1 over lambda fourth, but 1 over lambda fourth means proportional to nu to the fourth power. So this is again a signature of this of scintillation, and or equivalently of the broadening of the pulse. Okay, this is something that I'm going to comment later on. So the bandwidth, the scintillation bandwidth, is hugely dependent on the wavelength, or equivalently on the frequency, in a way that to the fourth power. So the higher the frequency and the shorter the mutual delay, and we will see that this TC is also telling you, if you imagine you have a source which is not a steady source, which is not emitting electromagnetic waves in a constant way, but as a pulse. Again, we are considering the impulsive source. Let's suppose that the source just emits a pulse, very narrow pulse. Because of this effect, you see here as an observer, you will receive rays from different points, having different light travel times. So as a matter of fact, the typical delay between all the different rays will be set by this quantity here. But this quantity here is the reciprocal of the correlation bandwidth. So it means that Tau c, so the typical time scales of the observed pulse, will be larger for what? Not for larger frequency, but for smaller frequency. So the higher the frequency, the narrower the pulse. So the pulse will be observed as a broadened pulse, and the lower the frequency, or the higher lambda, and the higher tau. So the broader the pulse. I'll comment this again next. So all this is about point-like sources. So here, the scintillation is caused by the possible relative motion of what is within the blobs, and so what lies in the screen and source and observer. Still considering the source as a point-like source. What happens when I consider an extended source? So a source whose size is not negligible. Well, to investigate this, let's consider the simplest extended source we can think of. So a source which is made of 2 point-like sources. 2 point-like sources separated by a distance which I call L, which is this calligraphic L. So let's see what happens. Well, the corresponding angle here, so I just used the red color for the second source, for the upper source. The dashed line is telling you the direction of these rays, were they not in the case of no refraction. The solid line is just the refracting angle. You see that the tilted angle is the same, because the blob here I'm considering is exactly the same blob. So they are tilted by the same angle, and the angle is different because of the different position of the source. In particular, the angle is just L over R prime. L is the distance here, R prime is just the distance here. Okay? So again, because we are considering small angles. So the same angle is here. But now here, the distance, if you want to calculate the displacement in this plane here, so the displacement between the two rays due to the two different sources is the angle times the distance. But here the distance is R. So angle L over R prime times R is this guy here. L times R over R prime. So this is the displacement you measure here, due to the fact that you have not one source but two sources. So the two rays, due to the same blob, are displaced by. So of course this argument works for all the other rays. So as a matter of fact, you remember that when you consider the intensity along this plane by a distance which is greater than dc, the correlation distance, then it means that in that case, what happens? In that case, if you sum up, so the two rays are at the distance between them by a distance which is greater than dc, it means that they will smooth out the difference that you would measure instead in the absence of two sources but with just one. So if this distance between the two rays happens to be greater or comparable or greater than the critical distance here, the correlation distance, it means that you will see no more of the effect that you were measuring. So you will see no more of the fluctuations by moving the detector from one point to another. So it means that the correlation distance becomes somehow sensitive, or I should say the fluctuations that you measure do depends on whether the source is an extended source, is made of different point-like sources. So how can you calculate the critical? So it means that there is a critical size of the source, critical angular size of the source, beyond which essentially the scintillation gets quenched. So you see no more of the scintillation because the difference between the different rays due to the extended source along the plane where the detector lies gets comparable with the correlation distance. So as a matter of fact, the possible fluctuation that you measure are quenched. So the scintillation gets quenched. Let's work out this critical size. Well, the angular size of the source is the size of the source over the distance between source and observer. So again, we are talking about small angles. So L over total distance, R plus R prime. I call this critical size, angular size of the source. When the critical condition is satisfied? Well, when exactly, okay, this guy here, I just replaced, I just multiplied and divided by the same quantity, R prime and over R, here and here, okay, just the same. Well, when what? When this guy here is indeed what I expect in the, it has to be equal to the correlation length. So the correlation length here, this is the projected distance, as we were telling you. If the distance, if the angle here is L over R prime, the projected distance along the plane where the detector lies is this guy here. I want this guy to equal the correlation length, this guy here. So I want this to be equal to this y. That's the condition which defines the critical size, theta c. Okay. In that case, it means that the two diffraction pattern will overlap, will no more overlap significantly. Sorry. So it means that even if you move the detector by in that case by a displacement which gets comparable to with the correlation pattern with with DC, you see no more wild fluctuations in the intensity. But DC, we already found that is lambda over theta s prime. So by replacing DC lambda theta s prime, but again, this guy here, I remind you, this is a relation we already obtained. So all this guys here is 1 over theta s. So summing up, we found that if the source is point-like, so has a negligible angular size, you are expected to see fluctuations as long as you have, for example, relative motion. There is some turbulent medium in the screen here. But if the source is not point-like, but is angular, but its angular size is comparable with the critical size theta c, or even larger, in that case, the fluctuation that you would observe due to the turbulence of this medium are significantly suppressed, quenched. So what's the condition? The condition is you can calculate theta c. So theta c, you see, it depends on the distance between screen and observer, on the wavelength you are observing it, and on theta s. Theta s, in addition to depending on the wavelength, it depends on the property of the screen. So on the blob size, on the width of the screen, and it doesn't depend on the source, essentially. And doesn't depend on the distance from the source. So this is a powerful way. If you can monitor the fluctuations that you measure due to the turbulence, the cause for fluctuations of the turbulence, the motion of the screen, and you measure at some given wavelength here, the fact that you measure, and so you can immediately calculate the critical size, angular size. If you do measure fluctuations, it means that the source angular size has to be smaller than, so the source cannot be too extended, let me say. So its angular size cannot be larger than theta c. Otherwise, you wouldn't observe wild fluctuations, so significant scintillations. And this is indeed very familiar with something. Should be very familiar with something that you know. So let's consider in the optical regime. You know very well that because of the atmosphere, you can think of the atmosphere as the turbulent medium. You know very well that the density in the atmosphere changes, is subjected to fluctuations. But change in density means change in the refracted index. So the atmosphere behaves like a lens, a changing length continuously. And because of that, you see that stars, not because they are intrinsically small, but because they are far away, so their angular size is much smaller than the critical size connected with the turbulent properties of the atmosphere. So you see there light, the flux that you measure, the optical flux that you measure from light with your own eyes or whatever, fluctuate or scintillate. That's what people usually say, that's twinkling stars. So stars twinkle because of that, because their angular size is negligible compared with the critical size associated with the atmosphere. While you know very well that planets do not as much as stars do, because planets, the angular size of planets is comparable or even larger than the critical size. So the scintillating effect is much more suppressed. So that's why you see a much more stable, much steadier flux in the case of planets, because they are extended sources. And so their angular size is comparable or even larger than theta c. So that's exactly the same effect. So you see that indeed for an extended source, and if you know the distance of the screen and the properties of the screen, you can immediately infer or set limits or infer about the angular size of the source you are considering. And here, and this is the very last thing I'm going to comment, is a very, very elegant example of how people exploited in the case of a cosmological source in the radio band, how they inferred a very important property. So what I'm talking about, well, what is this plot about? Well, this is just radio flux density. In this case, the unit is microjunsky. In the radio band, as a function of time. Time is measured in days. Days after what? After burst. Well, there was a gamma ray burst. So I will be talking extensively about them in my optional course. For people who are not interested, just imagine an explosion. By the way, an explosion due to a star which just collapsed, its core collapsed, and then just all the outer layers have been expelled. In particular, there is a source which is expanding, we know, at ultra-relativistic speed. This expansion shocks the interstellar medium, so the medium which surrounds the source. So there is a shock wave developing, and this shock wave emits radiation because part of this kinetic energy turns into radiation because of some properties. By the way, there is also synchrotron radiation, and we know that. So you know everything in principle to appreciate what happens. But this is not the point. The point is that you have an expanding source. Now, the source is at cosmological distance, so gigaparsec away. We are talking about something which is gigaparsec away. So at the beginning, you see, you are observing a source which belongs to a galaxy which is far, far away in the universe, gigaparsec away from us. But you have also a screen. The screen lives within our own galaxy, which is due to the plasma that we have in our own galaxy. And this plasma is subject to some inhomogeneous in density and turbulence as well. And so what means, given that the scintillation properties, in particular the critical angular site of the galactic plasma is known, particularly for any possible directions, is known from just by studying the galactic sources which lie within our galaxy but behind these screens. We know that, we know the properties. We can constrain the properties of the screen. So you know the properties of the screen, so you can estimate the critical size, the angular critical size. And so what happens? You see the flux. At the beginning, the flux is fluctuating wildly. You see here is by a factor of 2 or 3 on a relatively short time scale. And from a given time on, the fluctuation just are significantly quenched and significantly reduced. You see here, there are wild fluctuations, and from that point here, kind of 25, 30 days on, nothing more. Very, very much smaller fluctuations, smoother. So you clearly see that here something happened which significantly changed the behavior. Well, the interpretation was that, okay, this is the result of scintillation due to the plasma that we have in our own galaxy, so which is relatively close to us, few kiloparsec away from us, so relatively close to us, and for which we know the critical distance. So getting back to here, you know this guy here, but sorry. But in this way, if you assume that the reason for which the reason that explains that at some point the scintillation stopped is that you have a size, you have a source which is expanding, and at some point its angular size is no more negligible with respect to the critical angular size. So it means that if you interpret what happens here at the transition between scintillation and no more scintillation, you say here, okay, here is the time at which the angular size of the source has grown enough to be comparable with the critical size. Because I know that for sources whose size is larger, is greater than the critical size, I am expected to see the flux scintillating much less. But in this way, you know the critical size, so they estimated that at this point, the source has expanded in such a way that its angular size was 3 micro arcsecond, which is an incredibly small angle. You cannot measure directly. So you exploited the scintillation due to the interstellar gas, so something which lives very, very close to us, to infer about the size. And given that we knew at the time the distance of this gamma ray burst afterglow, so you know the distance, you know the angular size, you can calculate the size, the physical size of the source. But you know when it started, because this was kind of 30 days afterward. So you know the size of something which is expanding, and you know how long it took. So you can measure the velocity. And the result was that the expansion was an ultra-relativistic expansion. So the speed was very, very close to the speed of light. So this was directed, this effect, the effect of scintillation due to the plasma inhomogeneities within our own galaxy, was a very smart way to measure the size of this incredibly far away source and to say, okay, this is indeed expanding at ultra-relativistic speed. This is very close to the speed of light. Very elegant, very powerful argument. So you exploited the transition from scintillation to no more scintillation to constrain and to infer about the size, the angular size of the source, just because you know very well the properties of the screen in this case. Okay, because you have the opportunity to study the same screen on many other different sources which belong to our own galaxy. Very beautiful. So I know that this is kind of very detailed. We saw many different aspects. Of course, one has to go through in on their own to appreciate better the details. Of course, needless to say that I'm available for clarifications as soon as you need them. And okay, so on Monday, I will briefly touch upon a very beautiful applications of all of the effects that we've been exploring so far. And this, I'm talking about fast radio bursts. I will spend just not too long. Just I will touch upon the main aspects of this topic. Why? Because this topic is one of the hottest topics of the current research. It's been attracting a lot of interest. They have been discovered kind of 13 years ago, more or less. So they're relatively recent. There is a huge amount of progress that's going on, and I think you should know at least the very basics. And this is also a very beautiful application, so you can appreciate the amount of information that can be inferred from now the knowledge of what happens to an electromagnetic wave which crosses plasma and with or without magnetic field. So for today, it is all. That's all. So unless you have questions, I'll stop here.